Okay, so let's think about an example. Assume that the systolic blood pressure of 30-year-old male is normally distributed. So in the question, they are giving you that this is normally distributed with an average of 122 millimeter mercury, that's the height of it, and a standard deviation of 10 millimeter hydrograms mercury height. So you have the mu as 122 mmHg, and also you have sigma as 10 mmHg. So these data values may come from national level experiments or national level things you do, like you are finding some, you do a survey and you know that in this population you have a mu of 122 and a sigma of 10. So this is known. Okay, so these things are known, like the height of a Sri Lankan person, height of a SL person is 160 centimeters average height. So this is the mu. Similarly, the normally distributed average one for the blood pressure is 122. So this is known, and you are doing an experiment at the laboratory or at the hospital, and you have a random sample of 16 men. So you check 16 men. You use 16 men and do the blood pressure test from this age group. So the age group is this one. So it's basically, you are assuming that you are taking a sample from this normally distributed set. You are simply taking some sample. You don't know what the sample is. Take some sample and you are doing a descriptive statistics test. You are doing that, and then you checking the average blood pressure. So you don't know how it will go. You are going to check that. Now the question is, what is the probability that the average blood pressure of the sample will be greater than 125 millimeter mercury height? Okay, so how do we know that this is going to happen? We need to check, first of all, 30-year-old men. So they are having mu and sigma like this, 122 and 10 millimeter height for mercury height. And then you need to check, all right, we have 16 men with us. We don't know their mean. We don't know the sample mean yet. So we just need to see what is the probability that that sample mean is going to be greater than 125. So this is what we need to know. Probability of X bar, that is our sample, being greater than 125 millimeter Hg. So since in the question itself, we know that these are normally distributed. So Z X bar is equal to X. We can follow this, right? This concept, that X bars are normally distributed. So this comes from central limit theorem. We know this one. So sigma X bar is having a standard deviation of sigma divided by square root n, and X bar minus mu comes on the numerator. So this is what we know. Okay, so this is what we know, and we are going to check whether X bar is going to be greater than 125. So first step is you need to put your known values here. So we know that mu is 122, sigma is 10, our n is 16. 16 men were there, and we need to check how X bar, whether the X bar is going to be greater than 125, and what is the probability of this being true. X bar greater than 125, you just simply do this one and convert this to Z value. So how do we convert X bar into Z value? You need to first reduce mu and divide by sigma of X bar. And you have to do the same here. Okay, because it's a positive, sigma is positive, this sign is not going to change. So X bar minus mu we don't know x bar. So we don't know any of this, but we know that if we do this one, this thing will be converted to a z value. Okay, we know that this is going to be converted into this one. Now we are dealing with this value. We know that 125 is given, and the mu is 122, which is also given, and sigma is 10, that is also given. And we know that sigma x bar is actually sigma divided by root n. So we know 16 is there and sigma is 10. So 10 divided by square root 16. So when we do that, we get a set value of 1.2 here. And we just need to check what is the probability of this set value being greater than 1.2. So same thing, we refer to the table. We have now I'm following this table. This is a table that I usually follow. So the values are given to the left side. So z, if you know a z value, you know the area to the left of that value under the curve. So we know that the set value has to be 1.2, and 1.2 can be read by the table. So we go down and 1.2 is there. There is no decimal point. So the value is 0.8849. That is the z value under this curve. So 0. The z value you get for the area under the curve, you get for z equal 1.20 is 0.8849. 0.8849 is for the area under the curve less than 1.2. So this part, this is z less than 1.2. This is the area you get. However, what you need to find is z greater than 1.2. This is what you want to find. You know the area under the curve here, but you need to find z greater than 1.2. So to find that, what you can do is, you know that the full area under the curve is 1. If you reduce this part from that full curve, you get the area under the curve for the other part. So 1 minus this value, that will give you the area under the curve for this part. So that is 0.1151. Therefore, the probability of your sample of 16 men sample having a sample mean greater than 125 is 0.1151. So this is the way you actually find how sample mean can be a value greater than or less than a given value. So this is a very simple step. So if you are asked to find a simple question, let's think about a question, this type of a question. If you know that the strength of concrete is following a normal distribution with a mu of some 150 megapascals and a sigma of 10 megapascals. Okay, this is the normal distribution. And then you are asked to calculate, you are doing some sample testing. So you are doing a sample test. You take say 25 samples, and what is the probability that these samples have a strength greater than mu? So obviously the question is, what is the probability that the sample mean is greater than 150 megapascal? You can obviously understand this one without even doing calculations, because we know that the normal distribution, standard normal distribution, is symmetrically distributed. So you need the area under the curve here, but obviously when you know the mu, you know that this is 0.5. So you don't even need to find or refer to the table. But if some other question comes, like what is the probability that you get a sample mean greater than 170? So in order to find that, what you need to do is you need to follow the same thing, x bar being greater than 170. So you first of all reduce the mu and divide by the sigma of the x bar, and this is greater than 170 minus mu divided by sigma of x bar. Now you know that if you do this part here, this automatically converts this to a z value, z of x bar. We just need to find the value here. So 170, we know that the mu is 150 given by the question, and sigma is 10, right? And then you know that sigma x bar is sigma divided by root 10. Remember that, sigma divided by root 10. So n is 25 samples. When you include this one, you get a z value, some z value here, and you just need to find that z value area under the curve following the same routine. So it's just like a practice. If you understand how to do one, you can follow the same routine to understand and do the others as well. So I hope you can understand that it's not difficult. If you understand how to read a z table and a z value, then you can do most of the calculations related to hypothesis testing and all. All right, let's look at this question. A random sample of 16 men from this age group, which is that 30 to 30-year-old men. So that is the sample there. So a random sample of 16 men from this age group had their blood pressure measured. Calculate the probability that the average blood pressure of this sample will be between 118 and 124. So this is a very good question. So we know that mu is 122 and sigma is 10 and the sample size is 16. These were given. The question asks us to calculate the value being between 118 and 124. So this is what we need to find, x bar being greater than 118 and less than 124. So the probability of an x bar average value being in between these two values is going to be calculated following this one. You know that we need to find a value, like in your concrete strength example. You need, the supplier wants you to find what is the sample concrete strength being the probability of them being in between these values, for example. So how do we find that? You simply convert this entire thing into a standard normal distribution. So how to do that? You need to reduce mu and divide by the sigma x bar, and you do the same thing for this, divide by sigma x bar. These are positive values, therefore the sign does not change. So 124 minus mu divided by sigma x bar. So you know that this is going to be a z value, and you need to calculate this one and this one. So you get a value like this here. So in this case, I got a value P, the probability of Z being greater than negative 1.6 and less than 0.8. So how do you find this one using the table? I'll show you a simple trick. So if you want to find this one, if you want to find the probability of a Z value being greater than this and less than this, what you need to find is actually an area like this. So draw the area like that. So Z is going to be greater than negative 1.6 and it should be less than 0.8. So the area that you need to calculate is this part. Okay. So visually think about what you need to find. If you understand the visual, you can see that the area under the curve, what you need to find here is somewhat like this. If you can read the table and get the value of Z being less than 0.8. So you get the whole area here. And you need to reduce this small tail here so that you are going to restrain this part. So if you can reduce that area, that is the value of z being less than 0.16. If you can reduce this part from this, that will exclude this little tail here. So when you exclude this tail, you are ending up with this area. So this is what I have done. Z value less than 0.8 minus Z value less than negative 1.6. Now, when you are reading the values from this table, you don't have negative values. So how do you calculate negative values? Negative 1.6. If you want to calculate negative 1.6, you are looking for a value here, Z being less than negative 1.6. But you only have Z values greater than 0. So in order to find this one, you can actually follow the principle of symmetry. You know that the axis is symmetrical along, the distribution is symmetrical along the axis here. And you are looking for area under this part where this is negative 1.6. You are looking for this area. In order to find this area, if you know that this area is symmetrical to the area here to the right side, that is greater than 1.6. However, because of the table is giving you only the area to the left side, you cannot calculate this area. But what you can do is, you can calculate this area. Estimate this area from the table, less than 1.6. So 1.6, Z being less than 1.6 is 0.9452. So that is this area. So how do we calculate this part? We just need to simply 1 minus this area, that is 0.9452. You will get the area under the curve here. So if you know the area under the curve here, you can safely assume, actually you know, that the area Z being less than negative 1.6 is the same. Okay, so that is how you calculate an area less than a negative value using this table. So always when you have a Z table, check how the Z values are given. Now in this case, I know they are given for positive values greater than 0. Okay, and also not a fraction, it's the whole thing. Sometimes I told you they are giving only a fraction part of it, but in this case they are giving the full. Okay. I don't know, like maybe because of the internet connection, you get this problem. Some of you are complaining that you cannot hear and see the screen. There's really nothing I can do. Okay, so I'll just follow along. You have the recording, so you can later check that out. Okay. All right. So where was I? Okay, so this is the idea of sigma value. Calculate the probability that the blood pressure of an individual, this population will be between this one. So we did a similar calculation. Okay, so this is the idea of sampling and sampling distribution. So what you need to remember is that when you have a sample, according to the central limit theorem, the sample mean belongs to a normal distribution. Okay. First point, sample mean belongs to a normal distribution, and you can check the mean by referring to the standard normal distribution. Because you can convert it. So if you have a sample mean, you have a sample number. So the standard deviation of the sample mean distribution is given by sigma divided by root n. So the standard normal conversion is given by sample mean minus the population mean divided by sigma over root n. So when you do this calculation, you are converting the value to a standard normal distribution. So once you have the standard normal distribution, you can calculate the value here, and that will be the value that you refer to the table. So from the table, you can get a value, and you can find the area, so you can give the probability. Vice versa, you can actually follow the same thing in a different way and do that. So let's get into the confidence intervals. So what do you mean by a confidence interval? So we did in the last part, we did a question like this. Remember, I will write down the same question and I will start from there. Okay, I will start right from here where I stopped in the last slide. So a random sample of 16 men from this age group, that is 30-year-old men, measured, calculate the probability that the average blood pressure of this sample will be between these two values. So we did that question. What is the probability? What is the probability that the X bar value is between 118 and 124? Okay, this is what we calculated earlier using this thing, right? This is what we calculated. So we got the probability is 0.733. Okay, so we got the probability is 0.733 something, right? So this is what we got.